materials, basically, if we talk about non-metallic, means that the materials such as ceramic, polymer, what else? Composite, those are non-metallic. Okay, first, let's take a look at the ceramic, and the learning outcome of this first lesson, is you should be able to define and classify ceramic materials, including traditional and engineering ceramic. The lesson number 2 is describe the mechanical and thermal properties of ceramic and cite some of their application. Describe processing method for ceramic. Okay, a little bit on processing. Okay, the processing process very much different compared to metals. So if we look at ceramic materials, actually ceramic has been used widely since many centuries ago. Okay, especially for the civil structure like a building. Okay, they are used in many ancient structures that have survived up until present day. The Great Pyramid of Giza, the Great Wall of China are some example of application of ceramic materials. So ceramic materials are inorganic, non-metallic materials that consists of metallic and non-metallic elements. Okay, the elements means that the atoms. Okay, the basic atoms that we obtain from the periodic table. Okay, for example, like aluminum. Aluminum is metallic, right? Aluminum, but when it's combined with non-metal, such as oxygen, it becomes alumina. Okay, aluminum is metal, alumina is non-metal. Oxygen is non-metal. Oxygen. Okay, so when they combine together with ionic bonding, or some of them are covalent bonding, it will produce ceramic. Okay, so ceramic, we have ceramic traditional ceramic, and we have synthetic ceramic, or structure or engineering ceramic. So if we look at the bonding, okay, just like metal, the properties of ceramic are determined by the type of atom present, the types of bonding between the atoms, and the way the atoms are packed together. Okay, in most ceramic materials, ionic and covalent bonding exist together, and the predominant bonding for ceramic material is ionic bonding. Okay, so this is an example of ionic bonding. We have chlorine, sodium, and chloride. When they bond, they form a crystal structure. Okay, sodium chloride and HCl. So NaCl is ionic bonding. Right. The crystal structure. Okay. Ionic bondings are non-directional. This non-directional structure nature allows the hard sphere packing arrangement of the ion into a variety of crystal structures. The packing of the ion is determined by the relative size of the ion, the ions present in the bonding, and the electrical neutrality requirement. Okay, each cation has to be surrounded by an ion. So the ionic radius of anion and the cation, okay, are represented by Ra, radius of ionic, and Rc, radius of cation, are critical parameters which affect the crystal structure. Because the cation give up their electrons, so it will become smaller than an ion, and consequently the ratio between the cation over the anion is less than unity, which is less than 1. The radius ratio determines the crystal structure of the ceramic. Okay, the cation is smaller than an ion. And the range between the different, the ratio, the RC over RA ratio, okay, if you obtain a smaller ratio, basically you will have coordination number of 3, meaning that one anion will be surrounded by 3 cation. Okay, so like these smaller tiny gray atoms surrounded by 3 giant atoms. Okay, this is the coordination number 3. Okay, 3 atoms attached to 1 atom. And then if you have the ratio between 0.225 until 0.414, basically you will have coordination number of 4. How does it look like? Okay, these tiny small atoms bonded with 1, 2, 3, and 4. Okay, on top. Okay, these 4 atoms. And this is example of gallium nitride. Okay, so how many atoms surrounded by the gray atoms? These atoms surrounded 1, 2, 3, and 4. And what about these atoms? It's surrounded by 1, 2, 3, and 4. Okay, so each atom surrounded by 4 other atoms. This is a coordination number. The coordination number of gallium nitride is 4. Okay, so basically the ratio, okay, RC over RA, or we write RC over RA within this range. And what about if you have larger than 0.414, you will have 6 coordination number. And this is an example of ceramic that being 6 coordination number, which is sodium chloride. Okay, so these tiny gray atoms surrounded by 6 atoms of another element. 1, 2, 3, 4, and 5, and 6 at the back. Okay, 4 around it, and 5 at the front, and 6 at the back. So we will have basically 6 coordination. And that's another ratio, which is larger than 0.7 until 1. We will have 8 coordination number. Basically, the atoms is located at the 8th corner of the cube. 1, 2, 3, 4, 5, 6, 7. At the back is 8. Okay, so we have 8. This is example. Okay, cesium chloride, which have 8 coordination numbers. So the green atoms surrounded by 1, 2, 3, 4, 5, 6, 7, 8. Okay, at all 8 corners around this atom of the cube. All right, silicate structure. Many ceramic material contain silicate structure, which consists of silicon and oxygen atoms bonded together in various arrangements. Okay, this is silicate. A large number of naturally occurring minerals such as clay, feldspar, and micas are silicates. And the crystal orientation is basically, for example, like kyolinite. Okay, kyolinite consists of alumina. Alumina is aluminium 2O3. A silicate is SiO4, and the H2O. Okay, let me see, SiO2. This is, let's say, so meaning that 2 O ataupun SiO2 silica 2. Okay. So how many oxygen? 3, 7, 8 because H 4. So this is 4. 4, 4, 12. 4, 8, 1. Betul? 9. Mana ini? Silica. Okay. The thing is, if we determine the crystal structure, it's repetition of the silicate mineral, which is in the tetrahedral sheet, okay, where the silica link through the oxygen atom to the alumina octahedral, okay, and there is a layer of water to before repeats, okay, layer of hydrogen and oxygen before it repeats for another set of silica and alumina. Okay, so it will repeat like this is one set and then bond together with another set. So it forming crystal structure based on the repetition of several compounds in the kyanolite. Okay, this is very complex shape crystal structure for the ceramic. Okay, for the amorphous structure, okay, like for example the glass also part of ceramic. Okay, glass have a highly disordered. When we talk about disordered, it is non-crystalline. So opposite to crystalline, we have amorphous structure. Okay, because of this amorphous structure, the glass will having a brittle properties. So ceramic are relatively brittle and hard compared to metal. Okay, this is due to nature of ionic bonding. Okay, so if metal, imagine metal, we don't have this kind of couple, right? So for ceramic, it have a couple which is ionic combined between anion plus cation. Okay, so let's say this anion, this is cation. When we give a load here, what happened is anion and cation is not bonded anymore. Okay, what happened is anion with anion and cation with cation, right? However, for the metallic structure, what we have electron C inside. Okay, the electron C inside. So the electron is a glue, okay, to bond between all their ionized metal. So there is no the bond is continuously, even though you deform it, you deform the material. So for ceramic, what happened is when you break the bond between cation and anion, what happened is they will move, the atoms move, and if cation meet cation, there's no bonding anymore. Okay, what happened is it will detach, the atom will detach. Okay, let's say this is the direction of the load, the break will occur, and if you look at the fracture, it's a brittle fracture. Yeah, it's a clear-cut fracture. So ceramic tend to be weak in tension but strong in compression. Okay, the elastic modulus of ceramic is higher than metal because ceramic are bonded either covalently or ionically. So in a ceramic, the electrons are ionically bonded. That's why ceramic tend to be good insulator. Okay, so there is no active electron move around it. Therefore, all the electron is occupied in the orbital of the atom. So there's no active electron that can be conduct the electricity. Also, as a result of their high bond strength, ceramic typically have a very high melting temperature, often much higher than metal and polymer. Traditional ceramic are made from 3 basic components: clay, silica, and feldspar. Clay makes up the majority of the ceramic body, and the most common clay mineral is kyolinite. Most clay products also contain filler, often quartz and feldspar. This is microstructure of the ceramic materials. So for the clay, it provides plasticity when mixed with water. Clay hardens upon drying and firing without losing the shape. And the silica increase the rigidity of the wear. So where it is so that it will not collapse at high temperature. And feldspar used as a flux in the firing. So the example of traditional ceramic, okay, we have glasses, brick, tiles used in the construction industry, and electrical porcelain in the electrical industry. Kitchen crockery is classified as a traditional ceramic. Okay, electrical porcelain used as a strain insulator in the electrical application. This is the insulator. Okay, some part of the engineering. The next part is the engineering ceramic. Okay, engineering ceramic is a modified ceramic that used for heavy industry. Okay, for example, here is the aerospace. Okay, each of NASA space shuttle has a coating of ceramic tiles that protect it from searing heat, which is up until 1,260 degrees Celsius, produced during a re-entry into Earth's atmosphere. Ceramic engineering is an important contributor to the modern technology revolution. Okay, it has high melting point but low density. Okay, for example, aluminum, aluminum, and this is the density of the metal, aluminum, iron, and gold. And shuttle tiles compared to this material, which is metallic, it is even lower than the wood. Okay, of course, if we apply for construction building, some of material such as the beam structure in the buildings, we prefer to use wood material because high rigidity but low density. Even the woods is lower than the aluminum. Recently, we use aluminum as a structure of the building. Some part we already replace wood with the aluminum alloy. However, for the shuttle tiles, it is even more lower density compared to the aluminum. So for the application, okay, for the heat flow, high temperature and cold environment. So conducting solid, okay, which if we use low thermal conductivity, we can even reduce the temperature when it reach the substrate. Therefore, we use high low thermal conductivity for the application at a high temperature. For example, in the ceramic coating for the combustion chamber, turbine, or whatever the require high temperature application, okay, more than 1000 degrees Celsius. Metal cannot sustain that particular temperature, but ceramic, it can sustain at high temperature. Why? Because it has high melting point. Okay, the structural ceramic typically consists compounds such as alumina. Okay, although you can see aluminum here, but when it combined with oxygen, it will become alumina, and this is ceramic. Okay, ceramic. Silicon carbide, silicon nitride. Okay, alumina is made from hydride aluminum, which is aluminum oxide, known as bauxite. Silicon carbide and silicon nitride are made by reacting silicon with carbon and nitrogen, respectively. Silicon carbide is one of the hardest known material used in make cutting tools. Okay, high performance brakes and even a bulletproof vest. Silicon nitride has excellent thermal shock resistance and high temperature strength. It is a representative example. It's used in silicon nitride bearing in the main engineering of NASA space shuttle. Okay, the bearing material used in the high temperature application. Zirconia or the zirconium oxide, suitable for the crucible for melting superalloy. For example, if you want to melt some metal, okay, this crucible, the container that you want to pour the molten material, to melt the superalloy, for example, nickel superalloy, the temperature is more than 1400 or 1500 degrees Celsius, even it reach 1600 degrees Celsius. So you cannot use normal crucible. You need to use high melting temperature crucible or the cast, the container, okay, the cast, the mold. Okay, this zirconia is usually used to melt the superalloy. Ceramic crucibles are chemically and physically stable at high temperature. Okay, the processing method. The deformation forming of ceramic is limited by inherent brittleness. Unlike metal, okay, if you want to shape metal, you have a basic shape. For example, you have a plate like this, okay, metal plate. You want to turn it into this shape. You just cut it. You cut this area, all right? You just cut it by blanking or cutting or any forming process, okay? Or meaning to say is the forming process for metal is quite easy. If you have this kind of best shaped materials for ceramic, you cannot just simply cut this. Okay, why? Because it is brittle. Naturally, it is brittle. So ceramic products are always formed by casting. Okay, it requires casting process. Okay, how? By forming powder, tiny powder, and you shape it into this desired shape. Okay, the powder you put in the mold, and then you do the next step. Okay, powder processing. You need to have a powder of ceramic, and then you put in the mold. You can do next forming process. Okay, one of them powder processing, slip casting, tape casting, and some example of ceramic processing. You have a raw material, okay, in the form of powder, and you put it in the mold to form it, and then you do a sintering, some kind of heating process that allow the bonding between the powder particles. Okay, and then you can do for the machining, minimum machining process just to do the surface finish, and you got a final product. So the raw materials you mix, for example, you have filler materials, bonding agent, and the main powder materials, and then you do a forming process. You put in any shape. You give a compression, a bit pressure to allow the particle pack together, right? So during compacting, what you can see is that it's distort. The particle is distort, and then if there is a required heat, you can heat to promote the bonding between the surface of particle. And then it's machining if necessary to get a final finishing product. Okay, and then do the sintering process, and next is finishing. Right. During the sintering, what happened is, okay, so you have a particle packed together, and if you heat, it will promote bonding on the surface of particles. Okay, it will eliminate during the sintering. At the third and fourth stage, you can see that the porosity is reduced, and you can see it's like a grain separated by the grain boundaries, similar to the metal. Okay, powder particles are after the number one is the powder particle after the pressing, and then particle coalescence and pore formation. Still, there is a pore, and then pore change shape, so the size is reduced, and the pore gradually decreased by diffusion to the grain boundary. So this is a phase diagram of ceramic alumina silica. Okay, ceramic materials are inorganic, which is non-metal materials. It consists of metallic and non-metallic elements. The elements, okay, meaning that, for example, aluminum, okay, those elements are metallic, and non-metallic is, for example, oxygen, nitrogen, carbon, okay. So when they bond together by ionic bonding or covalent bonding, it will form ceramic materials. In general, most ceramic materials are typically hard, brittle, with low impact resistance and ductility. So ceramic materials are usually good electrical and thermal insulator. Why? Because the absence of conduction electron. And thus many ceramic are used for electrical insulator and refractors materials. Ceramic can be formed by fusion casting involve the agglomeration of small particles. Okay, very short for the ceramic. I think that's all for now for ceramic. So we will continue with the next materials, which is polymer. So before that, let's take a break. If you have anything to ask, you may ask. Okay, let's take a break and we will resume at 3:50. Okay, this is, if we look at a metal, we can see atoms are bonded in the form of and forming a crystal structure. But if you look at the polymer, like the plastic board, the grain inside, or not really grains, the atoms is bonded by covalent bonding, and the bonded atoms are forming a chain, a molecule change. Okay, so it is a structure of elements inside the polymer materials. So polymer molecules are derived from a source called hydrocarbon. So in principle, hydrocarbon are constituent of the petroleum and natural gas. So the methane, for example, is a major component of natural gas. This is ethane. We heat, we can produce ethylene, a monomer. And these hydrocarbon molecules are the precursor to produce polymer. So for example, we have a monomer, okay, where the C is bonded with double bond. And if we break these double bonds, we can combine all this monomer to form polymer. Okay. So for example, we have original CH hydrocarbon bonded for forming polymer. And if we replace one hydrogen position with chlorine, we can modify the polymer and become a polychloroethylene. This is known as PVC. And for propane, for example, we replace H with CH3. So we will get polypropylene. Okay, another example, styrene, we replace with the aromatic rings, we will get polystyrenes. And then another interesting or new materials, not really new, but recent evolution of polymer. Okay, we get Teflon by inclusion of fluorine, okay, in the hydrocarbon bonding. So we produce Teflon, PTFE materials. And when we talk about the formation of polymer, how we synthesize the polymer, it is actually through the polymerization reaction. The polymerization reaction is a process in which the monomers combine together by chemical bonding to produce a very large chain-like or network molecule, which we call polymer. So the polymer can be produced through either addition of polymerization or number two, condensation of polymerization. So the addition polymerization is the monomer physically linked together sequentially. And in this polymerization process, a polymer formed by chain addition reaction between monomer that contain a double bonding. Remember the double bonding between the C. Okay, we break the double bonding and we let the single bonding active. And why? How they form the bonding? Because it is very active and it will find another single bonding. Example, please.
Polyethylene, PVC, and polystyrene are polymers, also known as plastics. They are all being produced with the help of Nourion's organic peroxides via a process called free radical polymerization. Let's take a closer look at how this polymerization process works and what these plastics have in common. Since polyethylene is one of the most common polymers, we will use this as an example. The raw material used in the process is ethylene, which is the monomer in this case. While monomer means one part, polymer means many parts. So polyethylene basically means many ethylene parts. But how do we get from one part to many parts? It actually takes 3 steps. The first step in the polymerization process is the initiation. When heated, the organic peroxide breaks apart in 2 radicals. These radicals start the reaction with ethylene. One free radical opens the double bond of an ethylene molecule and forms a new radical. Then this new radical opens another ethylene monomer, and this process continues, making the actual polymer. This second step is called the propagation. Now there's only one step to go to turn a monomer into a polymer, the termination. The polymerization reaction stops once the last radical of one polymer chain meets another chain with a free radical. Then they combine, and the polyethylene is finished. The production of PVC and polystyrene follows a similar reaction. Only the monomer, process temperature, and pressure are different. The production of PVC starts with the monomer vinyl chloride. The difference between an ethylene and vinyl chloride is that one of the hydrogen atoms is replaced by a chlorine atom. For polystyrene, the monomer is styrene, and here the difference is that one of the hydrogen atoms on the ethylene is replaced by a so-called phenyl group. We have just shown that while these 3 important polymers are different in composition, they all share the same origin. Nourion, we help make polymers.
Okay, so this is a method that basically involved in the addition polymerization. Just break the double bond between the C and it induce radical atoms, and it will combine and break another double bond and combine together continuous, okay, propagate until it terminates. So the second process is condensation polymerization. For this method, there are typically typical monomer containing of 2 or more reactive atomic groupings. In this process, byproducts such as water and ethanol will be released. Okay, this is the mechanism involved in this condensation polymerization.
In this video, you will learn how condensation polymers form, some examples of condensation polymers, and the uses of these polymers. Unlike addition polymers, where monomers react to form a single product, in a condensation polymerization reaction, not only is the polymer formed, but also a small molecule is eliminated or lost, normally water. Polyesters and polyamides are the 2 types of condensation polymer we will look at. We'll first look at polyamides. This is known as the amide link. It is formed when a carboxylic acid reacts with an amine. In the formation of nylon 6,6, we react a molecule with an amine group on each side, known as hexane 1,6-diamine, and a molecule with a carboxylic acid at each end, hexane dioic acid. Since both these molecules have long chain carbons, they are only complicating the visual structure. Let us remove these and replace them with rectangular blocks. You can now see the functional groups at the ends of each molecule, a carboxylic acid and amine group positioned next to each other. These groups react to form water, which is eliminated, and a large polymer molecule is formed, held together by amide links, hence the name polyamide. Nylon has many uses in the textile industry, but it is also a structurally sound material used in engineering, especially where low friction is required, such as in bearings or bushes. We can now look at polyesters in a similar way. An ester is formed in the reaction of an alcohol with a carboxylic acid. In this example, we will show the formation of polyethylene terephthalate, more commonly known as PET. Using the carboxylic acid benzene 1,4-dicarboxylic acid and the alcohol ethane 1,2-diol. Once again, since both these molecules have a long carbon chain that may confuse the overall structure, we will replace them with rectangular blocks. As you can see, when we align the two molecules, a carboxylic acid and alcohol group can react between the molecules, causing ester links to hold the large polymer molecule together, and once again, water is released. PET is commonly used as a plastic for drinks bottles, and polyester is used to produce fabric for clothing. Now, at the end of this tutorial, you should understand what condensation polymers are and be able to give examples of polyesters and polyamides along with their uses.
All right. Okay, next is the molecular structure. Okay, if we look at the structure of polymer, it is not similar with the method. Okay, for the polymer structure, it forms a random kink and coil of the large polymer molecule leads to entanglement, okay, just like a spaghetti structure. Okay, mechanical or thermal characteristic depends on the ability of chains to segment, chain segment to rotate. So a linear polymer is one in which each repeating unit is linked only to two others. The binding force of this entanglement change are weak. Van der Waals between the molecular and mechanical entanglement between the change. Okay, so it's just one single linear polymer chains and they just entangle. Okay, because it is one long chain like a spaghetti, and there's no real connection between one chain with another chain. Okay, so a very weak force, van der Waals force between the chain, okay, or the strand of a spaghetti, right? So it's considered very weak. Another types of molecular structure of polymer, we call it branch. Okay, branch polymer are defined as having secondary polymer chains that link to a primary backbone. Okay, meaning that one chain to another chain is really bound by a link. Okay, so the chain packing efficiency is reduced with the formation of a side branch. Okay, which result in lowering of the polymer density. Okay, you can see the main change, there are a branch. Okay, a branch. Okay, is forming a branch. So linear and branch is a differentiate between its ability to be recycled. Okay, so the density, low density and high density it depends on the polymer change. Branch is lower density and linear is higher density. Another is a cross-link. Cross-link is unlike a linear or a branch. Is one chain with another chain is linked together. Okay, so we call it cross-link. The strand of spaghetti just now is bond with the branch. The branch is attached. The end of the branch is attached to another chain. So cross-link bond is formed between monomeric units, and the synthesis is by non-reversible chemical reaction. So, for example, the vulcanized rubber. So, if you look at this, there is a branch, but some branch, for example, like this main strain. Okay, it has branch. The branch connect with another chain. Okay, so there are two chains. The branch of each chain connect to another chain. So the cross-link molecule structure, for example, we have a react with the sulfur. So the sulfur promotes the cross-link chain. So this is the first chain. This is the second chain. The cross-link attach one chain to another chain. Okay, how to promote this? By addition of sulfur. Another is network molecule structure. The network molecule structure are quite complex. It is complex polymer that are heavily linked to form a complex network of 3D linkages. These polymers are nearly impossible to soften when heating without degrading the underlying polymer structure. Okay, it form network, macam jaring. It's like a net. So if you look at the classification of polymer, we have two categories. One is plastic, one is elastomer. In the plastic, we have thermoplastic and thermostatic. For elastomer, we have rubber. So the thermoplastic is a plastic material which becomes soft upon heating. And when we pull it down, it will become hard. This material can be reheated and reformed into new shape and a number of times without significant change in their properties. Okay, most of thermoplastic consists of very low main change of carbon atoms covalently bonded together. So this is thermoplastic. Okay, for example, the plastic used for the water bottles, the Lego, and the container, coffee cup. Another is thermosetting. For thermosetting plastic, okay, form into a permanent shape and cure or set by a chemical reaction, and this final form cannot be remelted and reformed into another shape, unlike thermoplastic. Thermoplastic, if you have the final product, you can heat it up and turn it into a liquid and form it into a new shape. Okay, you can recycle it. But thermosetting, when you have the final shape, you cannot remelt it. Okay, and form another new product. But what happens is it will degrade and decompose if you reheat it, okay, at a very high temperature. Thermosetting plastic cannot be recycled. Okay, most thermosetting plastic consists of a network of a carbon atom and covalently bond to form a rigid solid. So the thermoplastic we use for for example, when we combine these two polymers, it forms a thermoplastic to glue these accessories, and then once it hardened, it will form a permanent joint between these two plastic. So as a glue, as a resin for glue, and then like this cup, this casing for the telephone. If you ever even see this kind of very ancient telephone. So the engineering polymer, okay, we use for car body, like ABS. Okay, of course it is weak compared to the metal car body, but it is among hardest polymer. Polyamide for machine components, and epoxy used as a metric for carbon fiber reinforced composite. So we use epoxy in the composite application. Okay, polycarbonate panels we use for the roof, polycarbonate roof. And of course, if we look at the mechanical properties of polymer, okay, it is ductile, and depending on their molecular structure, it can be brittle also. So what happened is when we introduce the load, tensile load, it will not break, okay? Because at that time when you induce the load, okay, the polymer chain will stretch, okay, and it will form necking, and it will fracture after all the chains is form a maximum stretching. Okay, at the maximum form, all of the chain is stretched. Okay, the behavior of polymer greatly depends on the temperature. Most thermoplastic polymer exhibit ductile nature, and both thermosetting and thermoplastic can exhibit brittle behavior. In the brittle state, the polymer chains are locked into place through a strong interlocking network, making plastic flow very difficult. So start to have a fracture at the maximum elastic, and the fracture promotes the cracking. And this is a brittle fracture behavior. It's a clear-cut fracture surface. So if we look at into the processing of the polymer, okay, we can use injection molding, extrusion blow molding, and for this kind of process, we have the pellet, okay, of polymer, and we inject, okay, injection molding. We inject, we introduce heat, we melt it, and we push it into a mold, okay, through the dies. And then extrusion molding is a similar to injection molding, but the final product is in the form of long structure, like pipe tubing, okay, PVC pipe tubing. So those are extrusion process, okay. But for the injection molding, you can see this is the mold, okay, of that consists of the shape of your final product. So in a summary, plastic materials are produced by polymerizing of many small molecules called monomer, and it's formed into a very large molecule. We call it polymer. And thermoplastic require heat to make them formable, and after cooling, they retain the shape they will form into. This is thermoplastic. Okay, and for thermoplastic, remember, it can be reheated and reused repeatedly. And for the thermosetting, okay, usually form into a permanent shape by heat and pressure, okay, during which time a chemical reaction takes place that bond the atoms together to form a rigid solid, like the glue glue, when we combine with between resin and hardener, we combine together, it will form a hard joint between, for example, your jewelry with, or if you want to bond between one component with other component, use the glue, which is consists of resin and hardener. So for this kind of forming, it involves a chemical reaction that take place to form final product, which is a rigid solid structure. And thermosetting, plastic are covalently bond throughout with strong covalent bonding between all the atoms. Okay, I think that's all for the polymer. And so we still have time. We can continue to the next module, which is module lesson 3 of module 11. I think we can finish up all the chapter by today. Okay, the next is composite. So this is the learning outcome where you should be able to define composite material and state their advantage over conventional materials, and describe the role of reinforcement material and the matrix and how these phases affect the properties of composite. And then you need to able to define polymer matrix, metal matrix, and ceramic matrix composite, and cite the application. A composite material is a material system that composed of mixture. It's just a mixture. It does not involve solid solution. There's no dissolved materials. Okay, it just mixed together of two or more micro or macro constituents that differ. Okay, differ in structure and /or chemical composition. They are essentially insoluble in each other and have a clear interface separation that's separating them at the interface. All right, this is the microstructure of glass fiber composite. Okay. And you can see the glass fiber composite surrounded by matrix, and the fiber is you don't see a diffusion at the interface between the fiber and the matrix. So this is what meant by structure of the composite. Okay, the glass ceramic, the epoxy. You can see clear separation between the ceramic and the polymer. So the interface is separated, clear separation. The composite material contains two phases, matrix and reinforced. Reinforced is, for example, like this long reinforced material. It can be particles, it can be fiber. Okay. So reinforcement phase provide strength, basically provide strength and stiffness with the composite, and the matrix phase is to bond and protect the reinforced phase together and distribute the load among them.
The outer skin of the world's biggest airliner, the Airbus A380, must be super light and super strong. So the designers borrowed an idea from the 12th century Mongol bow, combining two different materials to make a composite. In the A380, the first material is lightweight aluminium, but the second material must be incredibly strong to withstand high-speed impacts. So materials engineer Paul Hogg is about to show me a very special form of glass.
So I'll just put that in there, yeah?
Yeah, put it in the flame, sort of
So move it back towards the point of the flame. Keep rotating it to distribute the heat.
Glass becomes a liquid at around 27 degrees Fahrenheit.
You'll feel it begin to go soft and a bit sort of floppy.
Let's go and bendy.
Let's go now.
Okay. Wow! Wow! We're still connected. Look at that. We are still connected. You may not be able to see it, but we are still connected by glass.
That's a go. There we go.
This is just glass.
It's just glass.
So this is pure, ordinary glass that we've just coiled up again. Why is this doing this?
It's thinner and more flexible, but it hasn't got the defects and cracks on the surface, which is why you can coil it quite nicely without it snapping.
This is a glass fibre, and it's very different to ordinary glass. With no cracks, it's incredibly strong.
It's about 6 to 10 times the strength of steel.
If this was steel wire or something,
This would carry about 6 to 10 times as much weight as the steel wire would.
I'm mesmerised by this stuff.
These glass fibres can be woven like textiles to produce sheets of material. The next stage is to add liquid resin. When it dries, it sticks the fibres together to create glass in its strongest form. Fiberglass. Let's see if this window can be smashed. A hammer.
So I'll just hit it. That would have done the glass, wouldn't it?
I think it would have done. Try it. Don't be shy. Give it a good welling.
Glass fibres provide the strength. The individual fibres might break, but the cracks can't spread from one to another.
It's quite surprisingly tough.
Fiberglass is even tougher when combined in a composite with aluminium. It's called glass reinforced aluminium, or GLARE for short. The two materials are sandwiched together in layers. The aluminium provides stiffness, like the buffalo horn in the Mongol bird. Fiberglass is like the sinew in the Mongol bird. It provides the strength that aluminium lacks.
Okay, see, as the individual materials, the glass itself is very brittle, weak, but in the form of fiberglass, okay, whereas it's provided strength, but it will eliminate the brittleness. Why? Because the brittleness has been covered by the properties of the matrix. Okay, so basically the matrix materials we choose data materials that can absorb energy during the impact load. So unlike pure metals, okay, we consider as homogeneous materials. The composite is heterogeneous materials. The mechanical behavior of composite is classified either as quasi-isotropic or anisotropic materials. So anisotropic materials, isotropic materials, homogeneous and heterogeneous. Okay, homogeneous, for example, pure metals. Okay, and pure metal is isotropic. So homogeneous, if we have isotropic and heterogeneous, it's a layered like this. Okay. Homogeneous anisotropic materials is a discontinued reinforced materials, and isotropic heterogeneous is a reinforced materials. Okay, separate inside the matrix materials. So composite is a anisotropic or quasi isotropic materials like this, quasi isotropic like this one, or anisotropic materials. So in most composite material, the material phase is a material with low density. Okay, for example, the aluminum, we choose aluminum because it is low density, and polymer also low density. The strength and stiffness of the composite materials comes from the reinforced material. For example, the fiberglass. Okay, so carbon fiber is a ceramic, high strength and high melting point, but it is brittle as it is. So if we apply the carbon fiber as it is, we cannot utilize it high strength. Okay, because the brittleness is dominant. So if we combine with a polymer, we can have zero brittles but high strength. Okay, the zero brittle comes from the matrix materials. So if you look at this diagram, Young modulus versus density, okay, lightweight material is somewhere here. Okay, for example, like foams, but foams having very low Young modulus, very low Young modulus. Okay, if we look at the composite materials, okay, it is even lower than ceramic material, the density, the lightweight. Okay, however, the Young modulus is high, above 100 gigapascal. Okay, of course, technical ceramic is higher Young modulus, but it is heavier compared to the composite. And if you look at this diagram, it is a log diagram at the density value. So multiple times heavier for the technical ceramic, which having higher modulus Young, but the density of this the composite is very low. And if you look at metals performance in terms of the Young modulus is lower than the composite and heavier, much heavier than the composite. Okay, this one is composite, the purple color. Okay, because of the use of stiff reinforcement phase, for example, the glass fiber, the composite material have exceptionally high stiffness, and lightweight metric phases used to the low density of the materials. Okay, because of the amount and orientation of the reinforcing materials can be controlled, the strength and stiffness also can be controlled. So depending on the intended application, composite can be designed to satisfy specific physical, geometrical, structure, and mechanical, chemical, and sometimes aesthetic requirement. So in the category of different composite, it defined based on the matrix, the polymer matrix, the matrix, either it is polymer, ceramic, or metal matrix. So for now, first, the polymer matrix composite. Polymer matrix composite are composed of a matrix from thermoset, for example, epoxy, phenolics, or thermoplastic, for example, polycarbonate, vinyl chloride, nylon, and acrylic. Polymer are used due to their room temperature properties, ease of fabrication, and the cost, of course. The example of embedded reinforcement phase used in PMC are, for example, the glass fiber, carbon, steel, or Kevlar fiber. And the application widely used for the aircraft body and the sport car, okay, the composite body of the sport car, and the blades, okay, it is huge blade. The size is, it can even reach 15 meter, 20 meter, 30 meters, okay, depending on the application of this wind turbine blades. Okay, if they don't use composite, what else material they can use? A polymer or aluminum metal? Aluminum is very heavy and polymer is not stiff. You need to make it thick and wider if you want to use polymer. But if you use thick and wide, you cannot optimize the wind energy and convert it into energy. The wind and convert it into energy. So the optimum design is a tiny shape of the blade. Tiny shape of blade like this, you cannot make it from polymer because the high aspect ratio is too high and it is impossible to make it from polymer. So the only choice is composite materials. The next is metal matrix composite. We call it MMC. It consists of course, the reinforced material must be not metal. Otherwise, if the reinforcement material also metal, means that they are tendency to form a diffusion. So you don't really get composite. So non-metallic reinforcement material incorporate into the matrix that made of metal. The MMC are widely used in application where the operating temperature is between 250 to 750 degrees Celsius. And the metal materials used, such as metric, includes aluminum, titanium, copper, magnesium, and some of their alloy. So the reinforcement phase for MMC normally comes from another metal in the form of intermetallic, intermetallic or ceramic, such as silicon carbide and alumina. So MMC are always more expensive than the more conventional materials. And they are found where improved properties and performance can justify the added cost. For example, for expensive material, it's okay to have this kind of performance and with the added cost. They are found in aircraft components, space system, and high-end sport product. So okay lah, if it is expensive, it is for aircraft, of course, it is an expensive item. So we can use MMC. Okay, but for cheap material, it is not suitable to have MMC product. Okay, this turbofan was constructed by using MMC materials, providing a lightweight but still strong design with higher efficiency of the whole aircraft. Aluminum graphite composite piston and cylinder liner developed at UWM Center for Composite Materials. The inside microstructure shows that graphite, okay, this is graphite, the black one, a particle concentrated in the inner periphery of the liner. CMC consists of CMC is ceramic material composite. It consists of metallic or non-metallic reinforced material incorporated into the ceramic matrix. The good things about ceramic, why we choose ceramic as a matrix, because of the lightweight of the ceramic. So if the majority of the materials used in the composite, which is of course contributed by the matrix material. So if we use ceramic as the matrix, we can have we can utilize the lightweight, the hardness, and the thermal properties, thermal and chemical resistant properties of the ceramic. So CMC are widely used in application where the operating temperature is between 800 to 1650. Okay, unlike MMC are until 700, but CMC is more than that. Okay. So due to ceramic metric resistance to wear, CMC are often used in tribological applications such as automotive, brake system, and also elevator disc brake. If you look at this application, it's involved a friction, abrasion. Okay, so the main properties, main requirement for this kind of application is wear resistant. Okay, to obtain wear resistant, you need to have high hardness. High hardness. So, which material that having high hardness? Of course, ceramic, and it must be in the form of matrix. If the ceramic in the form of reinforcement materials, so the majority of materials is non-ceramic, so it cannot be applied for the this kind of application. But if the majority of material, which is the matrix materials, is made of ceramic, matrix material made of ceramic, then you can utilize the hardness properties, and hardness properties always associate with wear resistant. So that's the reason CMC is being widely applied for the this kind of applications. Like, for example, brake system, okay, disc brake, a trouble-logical application, which utilizing wear resistant properties. Okay, these are other applications. So the flexibility in design and the unique material properties of the composite give designer or engineer or architects totally new kind of possibilities to bring their ideas alive. It is possible to produce composite for specific purpose. Example, reducing weight, increasing the toughness, and better creep resistance. Okay, I think that's all for the module 11. We have covered all the three categories of non-metallic material, which is polymer, ceramic, and composite. And I think that's all for our course. And for the next week, for the next class, we can have a discussion on the tutorial. I will give you some tutorial. We discuss on the question for test 2. And also we will discuss the solution for test 1. Okay, in the next class. I hope you can see your marks for test 1 if it's already completed. I'm not really sure whether the examiner already complete all the paper, but for me, I already marked other section test 1 completely, because today is the deadline. So any question? No. If no question, I think that's all for today, and see you in on Wednesday. Okay?
Doktor nak tahu attendance, Doktor?